Earth moves through a crowded neighborhood. Our solar system is filled with a constant stream of drifting debris. We monitor the extreme ends of this spectrum, tracking massive, world-ending asteroids while the tiny dust particles safely burn up as shooting stars. But there is a middle tier of debris, objects roughly the mass of a large land animal, like a rhinoceros or an elephant. This cross-section shows the standard scientific assumption for these objects. As the rock enters, intense friction causes it to detonate as an airburst, fragmenting into harmless dust high above the ground. Because of this reliable destruction, planetary defense models relied on the atmosphere as a guaranteed shield against anything in this specific weight class. In June 2026, that assumption failed. A smoking impact crater appeared in an empty, arid desert. Analysis revealed a massive mathematical anomaly. An intact object weighing 6,000 kilograms, the weight of an adult elephant, had reached the ground. The event triggered immediate global reaction and intense speculation regarding the nature of the object. Hypotheses filled the information vacuum, ranging from classified satellite debris to an extraterrestrial artifact. For planetary defense teams, the survival of the 6,000-kilogram rock proved that the foundational predictive models of atmospheric entry are flawed. Investigators moved past the initial speculation to begin a forensic, physics-based reconstruction of the meteor's descent. This diagram shows atmospheric destruction by ram pressure. Entering at 40,000 miles per hour, intense directional pressure builds on the leading edge. This impenetrable wall of superheated gas infiltrates microfractures, ripping typical stony meteors apart from the inside. Yet the 2026 object did not shatter. It successfully absorbed or deflected this atmospheric crush. To survive this pressure, the Elephantine meteor required a structural composition rarely seen in the typical rocks of our solar system. This 3D wireframe scan of the crater's geometry allowed researchers to project a line backward into the sky, revealing the exact angle of descent. Fragments recovered from the site identified the material, almost purely composed of iron nickel. This high metal content makes the object exceptionally dense and practically impervious to the internal fracturing caused by ram pressure. Mathematical analysis of the crater also revealed a second factor, a steep, direct angle of entry. This graph compares flight paths. A steeper trajectory drastically shortens the time an object spends in the high-friction zone, preventing it from vaporizing. The combination of extreme elemental density and a direct trajectory created a physical loophole, allowing an elephant-sized object to punch through the atmosphere. This event has redirected the focus of global planetary defense infrastructure. It exposed a flaw in current monitoring algorithms. They are optimized to find massive size, assuming mid-mass objects will naturally burn up. Tracking systems must now be updated to calculate for elemental density and entry angle, even for relatively small objects. Spotting tiny, dark, highly dense objects in the vacuum of space remains a significant technical challenge for our current sensors. The 2026 meteor proved that space remains unpredictable. It demonstrated that the atmosphere is a filter, not an absolute shield.